All right, good morning, class. Welcome back from the short break of just weekend of 2 days. Today's lesson should be on simple alternating current. Though I've told you, we started having some revisions where we discussed a lot on vectors, how to find components of vectors when the resultant was given, and we taught you also how to find the resultants of vectors in the previous clips. So today we're going to change a topic where I know this topic is somehow strange. Even though you've done it, if you remember, you asked me questions on simple alternating current, and I promised you to discuss it after we finish our scheme, our syllabus. So now we are going to start discussing issues on simple alternating currents. An AC current is just, or an AC, which is called alternating current, it's just a current that is reversible. It is reversible, it can change over times. It has so many denominations, unlike direct current, which has single denomination and it doesn't change by time, or it doesn't change by any factor. While simple alternating current is a current that can change over time. It can change over a certain time and it can change directions and it stays longer than direct current. Now, there are some important keys that one of us to know under simple alternating current. Number one is root mean square value of a current. Root mean square value of a current. Root mean square voltage. Root mean square voltage. And we have what is called a peak voltage and peak current. After this, as preliminary stage, there are some things that need to be understood. That is the Ohm's law under simple alternating current, the impedance, the circuit of simple alternating current, where capacitor, resistor, inductor will be used to connect in that very circuit. These are the things we are going to discuss under this very. We are going to discuss these items under simple alternating current. Remember, simple alternating current, like I said, has a wave nature. It has a wave nature. Since it has a wave nature, any item or any quantity impedance that has a wave nature, definitely it will satisfy this very graph. It will satisfy this very graph. It will satisfy this very graph. So once it is like this, assuming the current is this, so the root mean square, or the normal current, or the current flowing through this very diagram will be equal to I naught sine Wt, and the voltage will be V equals to V naught sine Wt. So every wave nature quantity will definitely have this very equation. This is wave equation for current, this is wave equation for voltage. So in a nutshell, the root mean square of the current, will be V naught sine I naught, will be I naught sine Wt, and the root mean square voltage will also be V naught sine Wt, where this W is an angular speed, of the current, being it a circular movement, and this T is the time taken to reach some certain distance from the mean positions of the movement of the current. So this is how the root mean square, or let me see, the nature of the current flowing and the potential difference across the graph here. And this is what is called a current flowing, which is I equals to I naught sine Wt, and this I naught is called a peak current, while the potential difference is V equals to V naught sine Wt, and the V naught is called a peak voltage, while the blue here is not actually the W, it's omega. The omega here is the angular speed of the current and the potential difference there. So what we have now is the numerical values of the simple, the root mean square value of the current. The numerical value of the root mean square value of the current, there is R, okay, IRMS, which is root mean square, equals to I peak divided by root of 2. Also, the potential difference as root mean square values equals to V naught over root of 2. So when you evaluate this, it's going to be 1/2 times I naught. 1 over root 2 is the same thing as 0.707. Then I naught. Automatically, my root mean square value of current will always be equal to 0.707 I naught. This is the root mean square. So once you are asked to find the root mean square value of a current, when a peak current is given, you can use this very relationship to find your root mean square. Sometimes a root mean square current will be given to you, then you are asked to find the peak current. You can use this very relationship, simple. But in case of other cases, there are some certain formulas that somebody can use to find the root mean square values of a current or a peak current. But as far as this is concerned, this is how you can use, or this is the formula one can use to find either the root mean square value or the peak value. One must be given to find another. So also the potential difference. The root mean square value of the potential difference will also be equal to 0.70 V naught. So you see, this is the relationship they have. This is what is called the numerical values of the root mean square value of a current and the peak current, also the potential difference and the peak potential difference. There is nothing bigger and better than this. If you have any question, you can ask. Let's see how we can look into the Ohm's law related to the simple alternating current before moving down to the capacitive reactance. Inductive, we are going to look into Ohm's law related to simple alternating currents. Remember, Ohm's law is nothing but V equals to I R, where V is the potential difference across from one point to another in a circuit, while I is the current passing through the conductor or the circuit, and R is the resistance of the connected to the circuit or resistance of the cell, whatever it is. So that one is called an Ohm's law. So related to simple alternating current, you can use this to find the root mean square values. So the root mean square values of the potential difference here, root mean square values of the potential difference will be equal to I root mean square then times R. So you see, this is what the root mean square values of the Ohm's law. V root mean square equals to I root mean square then R. Simple as ABCD. So anyone here can be calculated. So sometimes when R is given, I root mean square also given, then you can use this formula to find your V root mean square. When I say I root mean square means the root mean square values of the current. V root mean square means the root mean square values of the potential difference. Or resistor is given, this formula can also be used. Circuits can be of many types. Number one, you can have an AC circuit with just resistor connected, just like this. Assuming this is the AC source with your resistors connected. So in this case, we can have the total impedance to be R maximum. The maximum R meaning the value of this R given to us. When you connect a resistor of 20 ohms, so the impedance in this circuit will just be 20 ohms also. Why? Because the impedance is just the oppositions to the flow of electric current. So resistor can give a maximum stoppage or deteriorations to the flow of the electric current. Sometimes a capacitor will be connected. A capacitor will be connected. If capacitor is connected, the circuit will have this, and the total oppositions will be the value of this capacitor. But in this case, we have what is called capacitive reactance, and the capacitive reactance is X subscript C equals to 1 all over omega C, and this omega is the same thing as 2 pi F. Substituting omega with 2 pi F, you will have what's called the capacitive reactance as 1 all over 2 pi F C. This is the formula for calculating capacitive reactance. Now, in case an inductor is connected in the circuit, the circuit will have a nature like this. The circuit will be like this with the inductor connected to it. So when an inductor connected as a letter L, it will have a total oppositions with the values of the inductor, but it has an inductive reactance which is X subscript L equals to omega L, and this omega is the same thing as 2 pi f. And 2 pi f is the value of the omega. By substituting the omega, the inductive reactance will just become 2 pi f. So this is called inductive reactance, while this one is called a capacitive reactance. All these ones are circuits of alternating current. When inductor is connected, resistor is connected, and capacitor. There are some situations whereby a resistor and capacitor is connected in the circuit, just like in this case. Assuming a series connections of resistor R and capacitor connected in the circuit. In this case, we have C here and we have R. The total opposition here will be Z, which is called the total impedance, will be equals to root of R square plus XC square. Do you see how it is? Also, this will be Z square equals to R square plus XC square. So when an inductor is connected to the circuit instead of a capacitor, it's going to have an effect like this. With L and R, the total impedance will be Z equals to square root of R square plus XL square. This XL is inductive capacitor inductive reactance instead of capacitive reactance. So inductive reactance and resistor will be connected to the total impedance when inductor and resistor is connected. So what we have is V equals to IZ, and this is R and L. So we have our current will be equals to V all over Z with resistor and inductor connected. And with this capacitor, we are going to have V equals to I, Z and R subscript C, Z subscript R and C. So what we have is I equals to V all over Z, R and C. So this is what we have if this is a capacitor. Now what we have is when the three of them connected in the same circuit. If the three of them connected in the same circuit, there is capacitor is here in series. So what we're gonna have is the total impedance, and the total impedance is Z square equals to a root of R square plus bracket XL minus XC. Somebody will ask himself why XL minus XC, and the vector representation, this is it. This channel is for resistor, and this channel is for capacitive reactance, and this channel is for inductive reactance. So since the two of them are in opposite direction, we can have this to be XC or XL minus XC, and what we have is R here. So the total of them, or their resultant, is called the total impedance, where we can have Z square to be equals to R square plus XL minus XC square. So this is where we come to this very issue, and this is the total impedance. Automatically your B is equals to I bracket root of R square plus XL minus XC square, or you can have V equals to I Z subscript R, C and L. So this is what we have with the three items or three devices connected in that very circuit with the alternating current source, and this is it. So what we have now is just some example. Whenever you want to calculate capacitive reactance, you find out that frequency F is given with some values, then C is also given with some values. Then I use this formula 1 over 2 pi FC to find the capacitive reactance. So I think we are going to find 1 or 2 examples under this, but should be in the next classes. But students, this has to be a reminder. I know you have done something like this. The main thing and the most important thing to hold in here is the summary of what you're supposed to know is I root mean square equals 0.707 I naught. V root mean square equals to 0.707 V naught. Again, also with V equals to IR, you can apply root mean square under this and O. You can apply peak values over this Ohm's law. Then again is reactance. What we have is capacitive reactance as 1 all over 2 pi Fc, which is the same thing as 1 over omega C. Then the next is inductive reactance, which is 2 pi Fl, which is the same thing as omega L. Next to know or to hold in here is the impedance across all the circuits. When two items connected, one item connected will not be regarded. But when two items connected, we have the impedance of resistor and capacitor. It's going to be square root of resistor square plus or resistance square plus capacitive reactance square. Also, when a resistor and inductor is connected in that very circuit, we are going to have the impedance as R square plus XL square. When the three of them connected, we are going to have the total impedance as R, C, and L to be the same thing as square root of R square at the total resistance plus XL minus XC square. So this is what you're supposed to know under simple alternating current. All this can be calculated simply. That we can have V equals to I, Z, R, and C. If all the resistor and the capacitor connected, we can also have V equals to I, Z, R, and L. When resistor and inductor connected, you can also have Z, R, C, V equals to I, Z or Z, R, C, and L. When the three of them connected in series in that very circuit. So I think for this or for the preliminary stages, this is what you need to know. So the next is the vector representations of these very items. Their graphs, they are lagging, they are superseding, and whatever it takes to be. This is what we have right for now. There are so many relevant information in so many textbooks. If you don't, or if you use your time quite the way you're supposed to use it, you'll find so many informations or relevant informations under this very topic, simple alternating current. Please, if you have any question, you can ask in the comment box. I'm going to entertain your question either instantly or after some times when I'm through with everything. So thank you very much. Let's see in the next class.